Hi friends, in this course we are learning about feature engineering for machine learning. Today we are going to look at binarisation, which is a form of discretization. Okay, so using this technique we transform a continuous numerical variable into just two values. We will do similar things for categorical variables as well, where we transform multiple categories into just two categories. Okay, so here I'm loading a library called nbblock, which is just for code formatting. It does things like removing the extra spaces, aligning the code, similar sorts of things. And then here we are loading a bunch of libraries. Let's go over them. So the random library for creating some data for processing, and pandas for dealing with data frames, and numpy for working with arrays, savpy for computing some statistics, matplotlib for doing the plotting, and finally scikit-learn for creating the binary features. Now this one, it just sets the style for plotting. Here we are setting some global variables for plotting. This one we are setting the figure size. This is the width and height. And then we are setting the font size for the font on the figures. Now let's get into the actual technique. Now imagine you are working on a predictive maintenance project where we get some sensor data. We use the sensor data to create features, to build some predictive models so that we can predict the mission failures before they actually happens. This is to reduce the downtime and reduce the cost, etc. Now here we have created a data frame with two values. This is the timestamp, and then we have the voltage. We have created these 120 points between 0 to 100. Okay. Now, let's say we discussed with the field engineer, and this machine, it has some range where it is considered to be operating under safe conditions. Okay, so the engineer has told us that the voltage should always be below 80 volts. Okay, so here what we are doing is we are creating a new variable called voltage safe. Is it safe or not? By computing if the voltage is below 80 or not. So if the voltage is below 80, then it's safe, otherwise it's unsafe. Okay, here we have created a string. We are doing the same thing, but instead of string, here we have created an integer. So safe means 0, unsafe means 1. Okay, then the transform data frame, it looks like this. As you can see here, whenever the value is below 80, it's safe, and whenever it is above 80, it's unsafe. And you can see the mapping between safe and unsafe, 0 to 1. Okay. Here we are just plotting the data. So this is our raw data as it is. As I mentioned, we have generated 120 data points, and the voltage is between 0 to 100 volts. This is the histogram. Now, out of these 120 data points, now we have about 90 times the machine is operating under safe conditions, and the remaining 30 times it is operating unsafe. So we have transformed this continuous numerical variable into a binary variable with values only 0 and 1 here. Okay. Now the reason for doing this is because the machine learning model, it does not have any domain knowledge. So by supplying this domain knowledge, by creating this additional feature, we are making it easy for the machine learning model to understand what is safe, what is not safe, and what can likely to lead to the mission failures. Okay. Let's look at one more example here. Now, let's say we are building a recommendation system for a songs recommendation, right? Here we have different customers or listeners data, and we have marked for each song how many times did they listen the song. For example, let's say it's a user ID 1. Now these are all different songs. Now this song, the user listened to it only once, whereas this song, the user listened to it 91 songs. And this one, the user did not listen to it, right? So we have generated some synthetic data. Now for the recommender system, we just want to input if the user liked a song or not. Now, how do we define whether somebody liked it or not? It's a bit arbitrary. Now, somebody who might spend a lot of time listening to songs might listen to the song hundreds of times, whereas somebody who spend a limited time might listen to the same song only a few times. That does not mean that second user liked this song less compared to the first user. Okay, I hope you get that point. So that's why instead of these numbers which can vary from 0 to any big number, we want to make the recommender system job easier by simply saying whether the user liked the song or not. Now, we are defining like by if the user listened to a song more than once. Okay, if the user listened to a song a second time, which probably means the user liked the song. Okay, so we are going to transform this continuous variable, which can be anywhere between 0 to any high value, to just like or dislike. Okay, so here what we are doing is we are taking the listen count, and if it is greater than 1, we are taking that as the user liked the song, otherwise unlike. Okay, so here we have created a string variable, and similarly we can create the integer variable. Now here we have used this numpy function where condition, so it's a custom code. You can use this binarizer function from the scikit-learn as well. So here we set the threshold to 1. So if somebody listened to the song more than once, then we take that as they like the song. Okay. Here is how we transform the variable. Now here we have the raw data. So the user listened to this song only once. So we are taking that as unlike and 0. Now this one, he listened to it 91 times. So we are taking that as like and 1. Maybe let's look at this one. User listened to it only two times, but we are considering that as like. So this song and this song are getting equal weight because we just want to input the model whether somebody has liked the song or not. Now this number is not necessarily a reflection of how much the user like. The reason is, as I mentioned, somebody may be spending a lot of time listening, might have big numbers, and somebody spending less time might have low numbers, but they may both like the song with same intensity, let's say, right? Okay, so here we are going to do some plotting. Here we have the listen count, so how many times each song is listened. So this has a values between 0 to 100. So some songs are listened by 100 times. Now here the number of songs. So as we can see here, most of the songs have listen count close to 0. So all these songs are not liked by the user. The second one, it's the same plot, but here we just zoom in to this part between just 0 to 1. So here you can see this is 0. So all these songs are not liked. This one listened to it only once. So even these ones are not liked. So from here, all the points on the right, we are considering it as the user liked the song. Okay. All right. And in the second case, we might have this positive one versus negative one. Let's say we are taking the customer reviews for a product, and we have this sentiment score, let's say between -10 to +10. Now, instead of giving the model that the sentiment score will be between -10 to 10, because -10 versus -7 might not be that different, right? We want to again find out whether it is a positive review or negative review. So we can simply check for the polarity by checking if the number is positive or negative. Okay, so this is the actual ray data. Here we have find out the polarity. This can be either negative or positive, and then this is the numerical version of the this categorical variable. Okay. Now similar plot. The code is provided in the description below. You can have a look at the code, and then we might want to binarize when we have outliers. For example, let's take this sensor data with the timestamp. So this value is between 0 to 1 more often, right? But sometimes we may have outliers in this data. For example, here we have an outlier which is way above the normal range 0 to 10. We have another outlier which is 47. Okay, so when we are building a model, these outliers, those may be genuine reasons. For example, again, if we take this as a sensor data, now it might be incorrect data, or it might be, or the data might be correct, but the machine is not working properly. That's why the sensor values are very high, or it may be indicating that the machine is about to fail, etc. So here, what we can do is, we will find out how many standard deviations away each value is. So we consider this feature distribution as normal distribution. Then we can find out from the mean of this variable how many standard deviations away each value is. So here what we are doing is, we compute the mean of this variable, and then we are going on the negative side, the 3 times the standard deviation of this variable. So we are setting that as low threshold. And similarly on the right hand side, from the mean, we are going 3 times standard deviation to the right side, and we are taking that as the higher threshold side. So basically, for this sensor, we are defining what are the safe limits. What is the low safe limit? What is the high safe limit? Now, again, we are checking for each value. Is it more than the high, or is it lower than the lower threshold? Okay. So we are measuring, is it an integer outlier or not? So if it falls below these thresholds, we consider this as an outlier. Otherwise, it's a normal value. We are doing the same thing, but here, instead of using the threshold low and threshold high values, which are computed using the formula, we are using the z-score function from the statistics, which basically does the same thing. It simply compute how many standard deviations away a value is from the given distribution. So here we are saying, if it's above 3 standard deviations away, we are considering that as outlier. Otherwise, it's not an outlier. For example, if we look at this actual data, now these values, those are not outliers, 2, 9, 7, 6, 3, etc. Whereas this 99 and 47 are clearly outliers. So we have marked those two values as outliers, and also in the numerical form, we encoded them as 1, whereas all the safe ones are encoded as 0. Okay. It's a similar plot. So this is where the actual distribution is. These are the sensor values between 0 to 100. So majority of the values are below 10, but we have couple of values which around this 45-ish, around this 100-ish, right? So if we count outlier count, 98 values are not outliers, whereas we have these two values as outliers. Okay, so essentially we have transformed this sensor variable into a binary one based on if it is an outlier or not. Okay, now let's come to the categorical variable. Okay, now let's say we have some customers data. So we have this customer or person ID, and then we have their age group. Now we have infants, toddler, child, teen, adult, seniors, etc. Now we might be building a model maybe to detect how likely somebody is to get disease, or maybe how likely somebody is to purchase a product, etc. Now depending on the disease or the product we are selling, maybe the seniors are more likely to buy compared to maybe the childs, etc. Right? So instead of having these many categories, we are using this domain expertise or subject matter expertise to transform these multiple categories into just two categories. So what we are doing here is we are transform this variable to have only two values, which are, is it the person a major or minor? So we are saying, is it a major or minor? Now in major, we are considering only the adults and seniors from this group, only the adults and seniors. And the rest, all these four categories, we are not going to consider them as majors. Okay, so those are not non-majors, right? Okay, so that's how we built this major or not string. Now, if we want to build an integer, we can create a mapping. So for example, for integer, toddler, child, and teen, we are giving it a value 0. For adult and senior, we are giving it a value 1. Okay, so this is how the transform data look like. This is the raw data, the second column. And in the third column, we have this major or not, yes or no. As you know, in machine learning, the models can work only with the numbers. This is just for our understanding, but the actual data we feed to the model will look like this, right? So 1 indicating somebody is a major, 0 indicating that person is not a major. Okay. All right. It's the same thing. So before transforming the data, we have these age groups and the count of the number of persons in each age group. Now, after transforming the data, we have only two categories, major and minor. Now here you can see the count of each category. So basically all these categories like child, toddler, teen, infant, they went into this one. And the senior and adult, these two categories, they are grouped into this yes major category. Okay. And another scenario where we could be doing this binarization is 1 versus all. Now let's say we are building a model to predict if somebody is likely to purchase the product or not, right? Some customer. Now here we have some demographic information of the customer. These are the 8 states in Australia. Now for each customer, we know their state. Now, for whatever reason, maybe this product is manufactured in a state called Victoria, and the Victorians are more likely to buy this product, or maybe because of the weather conditions, etc., this product is more likely to sell within Victoria compared to the rest of the states. Okay, so in such a scenario also, we can transform all these categories into two categories, 1 versus all, right? So here what we are doing is, if the state is equal to Victoria, then it is yes, otherwise no. Okay, so we have the raw data, the state, and then we have created a binary variable called is it a Victoria state or not. So all these, none of them are Victoria, so those are no. Let me check one with Victoria. Let me just run this for a second. Go back here. Okay, let's recreate the data frame. Let's rerun this. Yep, so here as you can see, we have a customer from Victoria and this is labeled as 0. Again, in machine learning, we work with numbers, not the strings, right? So we can transform this into, we can one-hot encode or binarize to 0 to 1. Similar to the above plot, here we have the number of customers from each state. In this one versus all, here we have Victoria, that's about 11-ish. So yes, so this is about 11, the total number of customers, and all the remaining customers are grouped into no, which is about this, let's say 90 plus customers. Okay, so those are the scenarios where we might transform a continuous variable into a binary variable, or we might transform multiple categories into just 2 categories. So this process is called binarisation. That's all for today. Thank you very much. Hi, this is a course on feature engineering, and today we are going to look at fixed width binning. So we are going to transform a continuous numerical variable into bins of fixed width. Okay, so here we are loading a bunch of libraries to generate the data as well as to process the data. These are covered in a bit more detail in the previous video, so you can watch them. And here we are setting some parameters for the plotting. Okay, so here we are generating the data. Now let's say we have customer data and we have the number of months the customer is with us. Now these customers are, let's say they are with the company anywhere between 0 to 120 months. So we have this 2-column data. Now there are a couple of scenarios why we might want to apply this binning method to these months. Now let's say we are building a recommender system or maybe a customer churn predictive model. Now, depending on how long the customers are with us, we might be offering them some discounts. So those who are getting the discounts might stay with the company longer or might buy the new product we are offering. Now, the way we offer the discount, let's say every 18 months, we offer some discount. So if the customer is with us for 18 months, we offer some level of discount. Then between 18 to 36 months, we offer another level of discount, right? So we want to be able to inform the machine learning model that using an engineered feature. So here what we are going to do is, here we have defined a variable called bin width is equal to 18. Now we are going to transform the data to this format. So if the customer is with the company between 0 to 18 months, we transform it to 1. If it is between 90 to 36 to 2, then 37 to 54 to 3, and so on. Right? So here we have the data in months. Now there are a couple of different ways we can do. We can use the floor method or ceil method from NumPy. Now if we use the floor method, the starting value would be from 0, whereas if we use ceil, the starting value would be from 1. So here we are simply calling the raw feature value and we are dividing with the bin width which we choose, and then we are applying either the floor or ceil method. So when we apply the floor, the index starts from 0 and our feature is converted into this bin number based on the bin width. Whereas this one using the ceil method, the index starts from 1. Okay. So here we are just plotting the raw feature as well as the transformed feature. So here we have the histogram of the number of months. Now we have somewhat uniformly distributed. So for example, we have 50 customers who are between, let's say 0 to 5 months, and also 50 customers, let's say they are also 60 customer between 115 to 120, like that. right? Now this is the transformed variable. So we have transformed these values between 0 to 120 into the values between 1 to 6. Okay, starting from 0, and here we have the number of customers. Okay, now the other way to do that is defining the number of bins. Okay, so rather than choosing the bin width, here we are choosing the number of bins. Now this is our data. So the minimum value is 0, maximum value is 120. So if we are choosing the number of bins as 5, that's going to give us a bin width of 24. Okay, now same as before, once we find out the bin width, either we can use the bin width along with this floor or ceil functions, or we can use the cut function from the pandas. Okay, now the cut function works a couple of different ways. So here we are providing our raw feature value and then specifying how many bins we want to divide this data into. Now, if we set this label as false, it will return an integer index. So this variable is going to be months bin cut. Now that is this variable. So the index starts from 0 and it returns this integer value. Now, if we call the same function without this labels is equal to false, so we are essentially enabling the label. Instead of this integer, it will return the boundaries, the bin boundaries. Okay, for example, this value 50, it's between 48 to 72 and its bin number 2. Now this value 4, this value belongs to the bin of boundaries 96 and 120 and that bin number is 4. Okay, now to the cut function, we can also provide the bin boundaries explicitly. Now these don't necessarily have to be equally spaced, but in this case, because we are transforming the feature to have fixed bin width, we are explicitly providing the bin boundaries with equal spacing. So this will also return the bin boundaries. Now we don't use these as features in the machine learning. Now we can use any one of these 3 features as a feature to train the models. Now, whether the index start from 0 or start from 1, it will not have any effect on the model. Okay. All right. Again, the same thing. This is our raw data, which we saw before. And after we transform the data into bins, this is how it looks like. Okay. That's all for today. Thank you very much. Hi. This is a course on feature engineering, and today we are going to look at custom binning. So basically, we are going to look at how do we transform a continuous numerical variable into custom bins. Okay. So in the previous video, we have looked at fixed binning method. Today we will be looking at custom bin width method. Now, in my experience, this is the more often the case as compared to the fixed bin width. Okay. All right, let's generate some data. So here we have some customer data and we also have some customer range. The age varies between 0 to 100 and we have generated 10,000 customers data, right? All right. Now again, we might be building a model to predict how likely somebody to get a disease or how likely somebody to buy a product or something similar, right? Something which can be based on the age. But let's say it does not depend on the exact age, but on the age group they belongs to. So in such a scenario, rather than using the raw age as it is, we might bin it into custom bins. For example, here, all the customers are the persons between 0 to 3. We are grouping them as toddler. Between 3 to 12, that's as child. And then similarly, between 60 to 100, we are grouping them as seniors. Okay. So now again, we can use the cut function from the pandas. So here we are providing the raw feature and then explicitly the bin ranges. As we saw in the previous video, this will give us the boundaries, the bin boundaries. Okay, so this value age bin custom range, this will return the boundaries. For example, the first customer with age 61, the customer belongs to the bin with boundaries 60 to 100. This one we define here. And similarly, maybe this customer with age belongs to this 3 to 12. So that's the 3 to 12. So that's using the cut function without explicitly providing the labels. Now we can, if we call the same function with the label names such as defined here, then it will return the labels in the form of these strings. Okay. Then, as you know, in machine learning, we don't work with the strings. Now we can convert these strings into the integers. We can either do one-hot encoding, or we can convert them into integers, because there is some order to it, right? For example, child are older than toddler, teens are older than a child, so on and so forth. So these are called ordinal categorical variables. So they have some order to it as well. So either you can convert them to integers like this, or you can use them as one-hearted encoded variables in the model. Okay. Now this is the raw data. So this is some 10,000 customers data, the ages we have, and here we are looking at the histogram. Now we have transformed this data into these 5 groups: adults, seniors, child, teen, and toddler. Okay. Now the other example, here we have again some customers data with their income, right? So we have their income. Now this income is between the range 20,000 to 250,000. Okay. And again, we are trying to let's say build a predictive model where the customer likely to buy a product, or maybe the customer, how likely they get some loan, etc. Right? For such scenarios, rather than the absolute income, the income group might make the model job more easier. Now, one of the other reasons why we might transform these continuous numerical variables into few bins is the interpretation becomes easier, because when we explain the results or interpret the model, it becomes easier to say when the customer income is high, these are the chances of them getting the loan. When the customer income is in the medium range, these are the chances of getting them the loan, right? So rather than working with these fixed numbers, we can convert them into some categories, which makes the model interpretation as well as learning easier. Okay. So again, we are using the same cut function from the pandas. So here we are providing the raw variable and without labels. Okay. We are simply providing the bin ranges, and these are the custom values, because the space between them is not uniform. So this will return the ranges. Now this is just for our explanation purpose, so that we can see this value actually fall into these two values, and so on. Similarly, this value falls into these values, so on and so forth, right? But we actually convert them into some categories. So here we are providing the bin names as well. So we can see the customer's income has been transformed into these labels like low, medium, high, and very high. Okay. Again, as before, because there is order to this variable, we can treat them as ordinal categorical variables, meaning we can either one-hot encode them, or we can transform them directly to integers. So higher the integer, higher the likelihood of getting the loan, etc. Okay. Again, we are just looking at the raw data as well as the transform data here. Here we have the raw data. As we know, as the income increases, the number of people with that income reduces, right? So there will be only few people with very high income, whereas in this group there are a lot more people. So we have transformed this into these 4 categories. So there are many people in this low income group. There are very few people in this high income group. Okay. Yeah. So those are the scenarios where we can transform a continuous variable into a categorical variable with fixed or custom bin width for various reasons, such as making the model interpretation easier. Sometimes the exact value might not be important, so maybe the group is important. So in such scenarios, we might apply such transformation. That's all for today. Thank you very much. Hi, this is a course on feature engineering, and we have been looking at various discretization techniques, and today we are going to look at quantile based discretization. Okay, so let's first understand what's quantiles are, and then we look at how we compute the quantiles for the given data. Now before that, the code for all these videos are in the description below in the GitHub links provided. So please do check out the GitHub links, and if you find any mistakes in the code, please do let me know. Okay. All right. Now let's open this image in Wikipedia so we can view it better. All right. So let's imagine we were given a normal distributed data. So the normal distribution looks something like this. Now we organize the data from low values to high value, going from left to right. Okay, so let's say we have organized the minimum value somewhere here and the maximum value somewhere here, and all the values lie in between with increasing order going from left to right. Now the value in the middle, we call it median, and compared to mean value, the median is not affected by the outliers because it sits in the middle. Now what sits here and here does not affect the median value, right? So we know what median value is. Now this Q1, it represents the value below which we will have 25% of the data. For example, let's say we have these 1000 numbers, we organize them. Now Q1 will be a value below which we will have 250 values, and all these 250 values will be lower than the value of Q1. Okay, and similarly Q3 represents a value above which we will have the 25% of the numbers. So the 215 values will be more than Q3 and they will all be sitting here. Okay, now between Q1 and Q3, this range we call interquartile range, and the remaining 50% of the data sit between Q1 and Q3. And within that 50%, 25% sit between Q1 and the median value, and the remaining 25% values lie between median and the Q3 value. So essentially, we are dividing the data into 4 bins, and each bin will have equal number of the values. Okay, so those are the default quantiles represents. Okay, all right. Let's go back to the code. Okay, so here we have a normal distribution. We are generating a normal distribution using NumPy with a mean of 50 and standard deviation of 10, and we are generating some 10,000 values. Now let's say these are some sensor values. As we know, this these some sensor recordings, they always lie around their the mean value, and the distribution will be a normal distribution with some standard deviation, right? So let's say we have recorded these values at different timestamps. Now let's look at how the raw data is. So here we have the raw data, we have the timestamp, these are the 10,000 values, and we have the sensor value. So the values are somewhere between 10 to, it seems like 90-ish, right? And the mean value will be around 50 because that's what we have used for the normal distribution, and then the standard deviation will be around 10. So the mean will be passing through this and the standard deviation will be around 10. Okay. So here we are looking at the same data as a histogram. So the mean will be somewhere here. It's 50 and the standard deviation is 10. So the standard deviation bit is from 40 to 60, right? That's two standard deviation, one on the left, one on the right. Now, so here we are computing the median using this pandas function. So it is close to what we have expected, 49.92, close to 50. Now here we are defining the quantiles. Now the these are the default quantiles, but they don't have to be always these. I'll show you another example. So here we are going to divide the data into 4 bins, and each bin will have equal number of values. So because we have 10,000 values, now each bin is going to have 2,500 values, right? So for the first quantile, these are the boundaries we set. So the lowest value up to this Q1, which represents the value below which we will have 25% of the data. Then 0.5, this quantile represents the median value, and above 0.75 we will also have the 25% of the data, and this represents the maximum value in the data set. So here we are printing these quantiles. We have computed these quantiles again using the pandas function. We simply supply which quantiles we want, and here we have. So as you can see, this 0.5, that should represents the median, right? So this 49.92, that is actually the median we have computed directly. Okay, so this is the median, and the Q1 value is 43 and the Q3 value is 56. Now from our data, the minimum value is 15.18 and the maximum value is 91.95. So that's how our data distribution is. Now here what we are doing is, in earlier videos we have looked at the cut function, whereas here we are going to use this quantile cut function. We are calling it with the raw feature, which is the sensor value, and then we are supplying the quantiles we want to compute, and then we are providing some labels so that they can be assigned to the quantiles. Okay, so after we have applied this transformation, this sensor quantile, this is how they look like. For example, the value 40, it belongs to the first quantile, 44 belongs to the second quantile, because we must have the 25th percentile or Q1, that's at 43, right? So this value belongs to the second quantile. So going back to this picture, so 40 will be lying somewhere here in this region, whereas we have 43 as Q1 and 44 is somewhere here. So that belongs to the second bin. Okay. All right. So that's how we have transformed the data, and then we are just visualizing the data. So here we have the raw data histogram. Again, our values are distributed from somewhere 10 to 90. It's a normal distribution with the mean value 50 and the standard deviation around 10. Now here we are looking at the box plot, which we saw at the top. So this orange one, that represents the median. It's about 50. And this one represents Q1. So there will be 25% of the values, which is 2,500 values between this Q1 and the orange value, which is the median. And similarly, another 25% of the values between the median and the Q3. Now above this Q3, we will have the remaining 25% of the values. Now don't worry about what this and these points are representing. We will discuss that in later videos when we talk more about outliers. Okay. So again, the same histogram. Here we are showing the quantile values. Okay. So this is the median value. This one is Q1. This is Q3. and this is the minimum value, this is the maximum value. So between this minimum value and Q1, we would have 25% of the data. So if you sum the height of all these histograms, that would represent 25% of the data. And between this Q1 and median, we have another 25% of the data. Between median and the Q3, 25%, and the remaining 25% of the data is between Q3 and the maximum value, which is what we are seeing here. So basically we have divided this data into 4 bins using the quantiles, so that each bin will have equal number of the values we have. Okay. So as I mentioned before, these quantiles, so those are the default quantiles, the 25th percentile, 75th percentile. But we don't necessarily have to divide the data into those default quantiles. We can divide them into the custom quantiles as well. So here we are dividing the data into 5 bins instead of 4 bins, with each quantile representing about 0.2 or 20% of the data. Okay, so this time we are going to have 5 bins. Now we are looking at the same plot. So these two plots are the same. Whereas here now we don't have the median because we don't have the 50th percentile. But this vertical, it represents the 20th percentile. This is 40th, this is 60th, and this one is the 88th, and this one would be the maximum value. So the number of data points between each two consecutive these red vertical lines would represent 20% of the data, because we have 10,000 data points. So that translates to 2,000 data points in each bin. Okay, so that's quantile based discretization technique. That's all. Thank you very much. Hi, this is a course on feature engineering. We are looking at various discretization techniques. Today we are going to look at Gaussian binning. Okay, so first let's understand what Gaussian binning is. Okay, here is a Gaussian distribution image from Wikipedia. So the Gaussian distribution or normal distribution is represented by two values, mean mu and standard deviation sigma. So using these two values, we can generate a normal or Gaussian distribution. Now, there are certain distribution rules this data follows. For example, from the mean, if we take one standard deviation on the left, on the right side, that will cover 68%, 68.2% of the data. So here we have the mean, and on the left, we are looking at mean minus 1 standard deviation. So this width cover 34.1% of the data, and similarly on the right hand side. Now from this 1 sigma to 2 sigma, that will cover another 13.6% of the data. Then 2 sigma to 3 sigma, that's another 2.1% of the data. Then after this 3 sigma, we usually have very small, just about a 0.1 on the left, 0.1% on the right. So as you can see, 68% of the values are within 1 standard deviation away from the mean. So that's what the Gaussian distribution represents. Now what we are going to do is, for our given data set, we are going to compute the mean, and we are going to compute for each value how many standard deviations away the value is from the mean, and that how many standard deviations away, we are going to use that for binning it. Okay, so here we are generating a Gaussian distribution with a mean value of 50 and the standard deviation 10. So mu will be 50, and the sigma, which represent the spread of the Gaussian distribution, is 10. Okay, so we have generated 10,000 values. Here we have, we can take this as a sensor or some other variable with time. Okay, now we are computing the mean and standard deviation here. So the mean 49.83 is close to 50. Now, as we increase the number of data points, the actual mean will be very close to the expected mean, right? Similarly, the standard deviation. Okay. Now, so as I mentioned, we are going to compute how many standard deviations away from the mean each value is. Now that is represented by a quantity known as z-score. Okay. Let me comment this. Okay. So the z-score from statistics, it simply compute how many standard deviations away from the mean the value is, and if it is on the left hand side, it returns with a negative sign. If the value is on the right hand side, it returns with a positive sign. So here we are computing this z-score, or you can say the feature standard deviation, the number of standard deviations. Okay, and then as I mentioned, it takes negative sign if it is on the left, positive sign if it is on the right. So here we are computing if it is on the left or right using this positive, negative, using NumPy aware function. And then finally, we are taking the absolute of the z-score, because we are only interested in how many standard deviations away, not the sign. Okay. All right. So this value is computed before running this code. So as you can see, it takes both the negative and positive values, and it gives this sort of distance, how many standard deviations away the value is. Okay. So here we are generating some images. Now this is our actual distribution. So as we expect, majority of the values are around 50 and the standard deviation is around 10. Now here the middle one that represents the sigma, and this one represents 1 sigma distance, 2 sigma and 3 sigma. Similarly on the right hand side, this one represents 1 sigma, this one 2, and this one 3 sigma. Now the same data we are plotting using a box plot. So this one will be the median. It's a Q1, Q3. 25% of the data points are above this Q3 and 25% of the points are data points are below this Q1. As we saw from here, the Gaussian distribution, it's a symmetrical distribution around the mean. So we expect the equal number of values on the left as the number of values on the right. So that's what we are looking at here, the positive number of positives and number of negative. Now the actual feature transformation we are doing with this Gaussian binning is this one. So we are computing how many values are away from the standard deviation. So out of those 10,000 values, so as you can see here, about 6,800 values, those are within 1 sigma standard deviation. So out of the 10,000 values we generated, 6,800 values, those are in this dark bluish area. Okay, and the second region is the 2 sigma width. Now that would be some 13.6 plus 13.6, that's around 27-28% values. So this is that value, and then 3 sigma, and usually the values outside 3 sigma are considered outliers. So we have very small fraction of values after 3 sigma. Okay, here we are looking at the same plot, but it's normalized so that we can look at the percentage. So as we discussed, so within 1 sigma we have about 0.68, that's a fraction. So 68% of the values are here, maybe some 28% of the values are in this 2 sigma region, 27%, and then the couple of percent, around 3%, are in this 3 sigma, and very small fraction, less than 1%, are within this 4 sigma distance. Okay. All right, that's the feature. So basically we have transformed this continuous variable into some discrete variable using how many standard deviations away each value is from its mean value. That's what we call a Gaussian binning. Thank you. Hi. Uh, in this video, we are going to learn about data discretization using K-means technique. Okay. So for that, here we are generating some data, 3000 data points using Gaussian or normal distribution coming from 3 different distributions with different means and standard deviation. We are doing that for visual and clarity purpose, easy to understand, but the data don't have to be this way. Okay. All right. So here we have the timestamped the raw features, and let's look at how our raw data is. Okay. So we have 3000 data points. Now these are the values. So the first one is again coming from a normal distribution with a mean of 50 and the standard deviation about 10. And the second one probably mean of 10 and standard deviation is 50. So the mean is somewhere here. And because the standard deviation is slightly higher, you can see the spread of the data is also high. And the third distribution, the mean is 170 and the standard deviation is 20, which is even higher than the second one. So that's why you see this spread, wider spread here. Okay, so we have this data. Again, for demonstration purposes, we have this almost clearly separable data, but in real world, we might not have that. Okay, so the K-means is a machine learning technique to cluster the data into different number of groups. But here we need to inform the model how many groups we want to divide the data into. Now we might not know what's the best value for that. There are other techniques to find out the optimal number of groups. But let's say we have already did that analysis and we know 3 is the optimal number of groups for this data set. So what we do is we call this K-bin discretizer from scikit-learn. We are saying, okay, I wanted 3 bins and I wanted to use the K-means algorithm for grouping or dividing the data. Okay. Here we have only a single feature, but this model expects a data frame or 2-dimensional array. So here we are simply reshaping it to multi-dimensional or 2-dimensional array. Okay. So at this point, we are only doing the fit. If you know scikit-learn, you probably know this language, fit and transform. So when we do the fit, we learn the task, whether it is training an ML model, which in this case we are training an ML model. And then when we do the transform, we actually apply what we learn during the fit to the data. So we do the fit on the training data, then we can apply the transform on training data, test data, or validation data, etc. Okay. All right. So here we learned how to divide the data into 3 bins. And now we are applying for each data point which bin the data belongs to. Okay. And it also returns this 2-dimensional array. So here we are flattening it to get back this 1-dimensional array. Okay. So this is our feature. This is the raw data. And this is the bin number. So it starts with 0. So 0, 1, and 2. So this array will take only 3 values, 0, 1, and 2, because we have asked only for 3 bins. Now let's look at how the data is divided into 3 bins, right? So these are the bin edges. So the first bin values lie between this 23 to 73. The second bin values lie between 73 to 132. And the third bin values lie between 132 to 233. Okay, so we are doing some plotting. This is the histogram of raw data. This is our actual data. Now this vertical line represents these 4 boundary values we have discussed. So the given the data in this blue color, the model has divided into 3 groups with the boundaries. So the first group values lie between values this and this, and the second group values lies between this and this, and the third group values lie between this and this. Now, if instead of histogram, if we look at the raw values as it is, so here we have the raw values, the 3000 raw values, and the first group values are between these two horizontal lines, and the second group values are between these two, and the final group values are between these two. So it seems like model has done a pretty good job. Now the points in the middle, those are clearly assigned to the groups they should be, and because of this overlap we have some points. For example, I mean these points, even though they are generated as part of the second group, but clearly they belongs to the first group, right? So the model is able to divide this data clearly into 3 bins. Okay, that's how the K-means. That's how we can use the K-means algorithm to cluster the data into different groups, and we can use the group ID / bin number as a feature as well. Okay, thank you. Hi, we have been looking at various data discretization techniques. Today we are going to look at another one called a Fisher-Jenks algorithm or natural binning algorithm. It also goes by a couple of different names you can see here. Okay, so it works somewhat similar to the K-means clustering we have seen. But internally it tries to reduce the variance within the group and tries to increase or tries to maximize the variance between the groups. Okay, so let's generate some data to test this algorithm. So again, here we are generating the data from 3 distributions. So this time we are using uniform distribution as well. In previous video we saw all 3 normal distributions. Okay, so here we have a uniform distribution between 90 to 110 in the middle, and also for the third normal distribution we have more data points. We have 2000 data points here, right? So this is our raw data, and this is the visualization. So the first one, it's a mean of 50 and standard deviation 10. This is the normal one, and this is a uniform distribution. As you can see, this is more tighter, and the values are spread uniformly from the lower to the upper bound, right? Unlike in a Gaussian distribution where 70% of the values are within this one standard deviation, right? Here we have the equal spread. And the final one, here we have more data points, double the data points, also higher standard deviation 20 with a mean of 170. Okay, now again, similar to the K-means algorithm, we have to decide how many groups we want to divide into. Now for a real world data set, they are not this clearly separable, so we might do some experimentation to find out the optimal value for the number of groups. So we call this algorithm Jenks pi algorithm with the raw features and the number of groups we want to divide into. Okay, so it returns these breakpoints or the boundaries. So the first group is going to be between the lowest value, maybe 15 to 75, and the second group going to be between 75 to 137 ish, and like that. Okay, and then we are going to use these boundaries to assign label to each data point using the pandas cut function. So to the pandas cut function, we are supplying the raw data and we are providing these breakpoints. Okay, and the labels we want to give. So we are going to give the labels as group 1, 2, and 3. Okay, so this raw data, first we have divided into different groups using the breakpoints and Jenks pi algorithm, and then we assign the labels. Okay, all right. This is how the binning looks like. So here we have again the histogram of our raw data, and these are the boundaries for each group. So the first group lies between these two red vertical lines are the values, and the second one and the third one. Now, if you look at the number of data points in each group, so the group 3, it has some close to 2000, maybe 1800 data points, right? So some of the values from group 3, those are assigned to group 2, so it's not exactly 2000. So some of the values from here, from group 3, are assigned to group 2. So that's why we are seeing more number of data points in group 2, more than 1000. Okay, probably some 100 points extra. Whereas group 1, which is clearly separable from group 1 and 2, it has the exact number of points we have when we constructed the data, right? So this one. So as you can see here, the group 1, it's a normal distribution spread from here to here. So the group 1, it has the exact number of data points as we generated, whereas some of the data points from group 3 has been distributed to group 2. That we can see from the below plot as well. Okay. All right. So this is, again, we are looking at the raw data points, these 4000 data points along with their bin boundaries. So the first one, first group, it's clearly separated. Only just 1 point from group 1 went to group 2, but that's clear. I mean, this is more closer to group 2 compared to group 1, right? Whereas a number of data points from group 3, because it has this higher standard deviation, so all these data points are assigned to group 2. Okay. That's it for today. Thank you very much. Hi, we have been looking at various data discretization techniques, and today we will look at a very simplest one called rounding. Okay, so here we have generated some 10,000 data points. Now this rounding method I have not used in any of my data science projects, but it might be useful to you, so that's why I'm mentioning it. Okay, so now this feature, it might be a fraction or it might be a percentage with so many digits. For example, here we have 6 decimal places, right? Now maybe this value 0.35474, right? It's not that different from maybe another value, let's say 0.35474.2, let's say, right? So we don't want to confuse the machine ML model with these too many values which are actually too close to each other and do not have any significant difference anyway. So that might be one scenario where we might want to use this rounding technique to reduce the number of data points, or to discretize this very highly continuous and highly decimal places data, right? So when we have these fractions or percentages with high number of decimal places, we might use this technique, right? So it's very simple. All we are doing is, for example, in case 1, we are multiplying with 10 and then just taking the round, right? Here you can take the floor, seals, etc., but rounding works best. Okay, and then in case 2, we are simply multiplying with 100 and again applying the rounding method. So here we have this value 0.35. In case 1, we are multiplying with 10, so that becomes 3.54. When we do the rounding, because it is closer to 4 than 3, so it's get rounded to 4. Now if we used the ceiling method, this value would have been 3. So 3.54, when we apply the floor, it will be 3, right? So again, choose which one you want to apply, but probably rounding is better for such scenarios. Okay, so that's all. We have this very continuous variable. We multiplied either with 10 or 100 and then we round it up. Now, if you look at the number of distinct values in each of these 3 features, so the first one has 10,000, right? So the number of total data points we have is 10,000, and each value is unique in these data points. So we have all 10,000 distinct. Whereas when we did the rounding with respect to this 10, so we are transforming all these values to just have a value between 0 and 10. So that means we have much fewer values. So we have only 11 values. Now, even if we have a million values here, in this feature 10, we would still have only 11 values, right? And similarly, when we use this 100 for multiplying the original data, that gives us 101 distinct values. Okay. So just some visualization. Again, we are looking at the data distribution, the histogram. So we have all these continuous values between 0 and 1, somewhat uniformly distributed. Now we have transformed this such highly continuous data into just these 11 values. So we have discretized this data into just 11 points. So as I said before, I have not used this technique in any of my projects, but you might want to use it whenever you have the fractions or percentages in your data set. That's all. Thank you very much.